So I want to quickly go over a voltage division example that I've seen students get tripped up on. We have funky resistors like this over here, so it takes a little bit of a simplification to solve this problem using only voltage division. So the first step is just going to be working out this side of the circuit, getting it down to be something that we can actually work with. So if we label our nodes like we normally should do, this node here we can call VA, which we know is just going to have the same voltage as our voltage source here. So we label that. And then call this VB. And VB is going to be equal to V out. The voltage across R6 is what we're interested in. And we see that VB is across R4, R5, and R6, meaning that they're in parallel, so they're all going to have the same voltage across them. So instead of having this really weird looking slanted resistor down here, which professors sometimes like to include in their problems, we can come down here and make it obvious for ourselves that R5 is just normally in parallel with R4 and R6. So now we can combine these resistors in parallel so we can set up our voltage division. So this combination, we're just going to use the normal parallel resistor equation, which is just your total parallel resistance. So 1 over R1 plus 1 over R2 for however many resistors you have. So I'm going to move this other problem out the way real quick. It's for a later date. So we're going to do R4, R5, and R6. R4 is 2.5K. And drop the K because we know it's kiloohms. R5 is 1 over 5. And 6 is 1 over 10. So just putting that into the calculator real quick. .42 kiloohms. So we can come back up to this circuit here and replace all of those resistors with one equivalent resistance of that value. 0.42 kiloohms. And this is still remains VB, which is equal to out here. So even though we simplified those resistors, the voltage is going to stay the same. Now, if the question was asking for like the current through R5 specifically, we would want to leave that alone, but we haven't messed with that. So we can come up here, and now when we look at this circuit now, we see that VA, obviously the potential of that node is the same across the node. So the voltage is actually going to be dropped once current passes through R3 in this mesh here. So our voltage division occurs between R3 and then this new combination that we created. So 1.42 is going to be our R2, R3 is going to be our R1, and the voltage that's being divided is VA. So we can come down here and write our equation. V out is equal to the source voltage, the voltage being divided. First voltage was 20. R2, 1.42K, and then R3 plus 1.42. R3 was 5. 2. I'll just put this in the calculator real quick. .42 volts. as our final answer. So now we can quickly check it inside of LT Spice. Make a quick little schematic and run a DC operating point. So I'll make the schematic with the original circuit without the simplification to see how accurate it was. And it is possible to put the resistors and wires diagonal inside LT Spice, but it's not really necessary. So come around here, get our values in. Ooh. 20. R1 is 10K. 2 is 10K. R3 is 5K. R4 is 2.5K. 5K. 6 is 10K. Always want to put our reference node. And then our V out is this voltage across R6 here. DC operating point. Close that. So it's giving us 4.44 volts, which is very close to what we got by hand. We got 4.42, LT Spice giving us 4.44. So it's probably just the only discrepancy could be the rounding and the simplifying the parallel resistors. So yep, that's how we do that problem.